Okay, thank you very much for coming to this talk. This talk is called Surprise! LM-generated surprisal values cannot fully account for human parsers' preferences in relative clause comprehension. My name is Nentcheva, and this is very much a joint work with Sebastian, Schuster, and Andrea Santi, who are also from the Department of Linguistics at UCL. So in this talk, I'm going to be presenting a structure, a relative clause with a non-local filler gap dependency, where the structural preferences of human parsers differ from the predictions made by computerized language models. And our motivations for exploring this case of divergence between the predictions made by language models and by human parsers is really to find out more about the predictive mechanisms which underlie human sentence processing by looking at how they're different from the predictions made by language models and then hypothesizing some potential explanations as to why. So by now, and in this conference included, we've seen a wealth of data which shows us that when humans are comprehending language, they're making predictions, right? So when we listen to or read linguistic input, we're not just passively waiting to see what word appears next in the input, we're all the time making predictions. And when our intuitions don't align with what actually appears in the input, we experience processing difficulty. And this observation has been formalized under surprisal theory. Surprisal theory suggests that the processing difficulty experienced on a word is proportional to its surprisal, where surprisal is the negative log probability of a word given the context. And surprisal has been massively successful in accounting for a range of linguistic phenomena. So recently, and very compellingly, we've seen evidence from language models which are trained on next word prediction. And there have been findings that these language models are able to generate internal representations which can account for a very large proportion of the variability in human neural and behavioral data. So on this visualization, we can see these GPT models on the right in blue can account for up to 100% of the variance in human fMRI data during the completion of a linguistic task. And this finding has also been replicated for behavioral data with self-paced reading times. And very critically, it's the ability of these language models to predict the next word and not their performance on any other linguistic tasks, such as similarity-based judgment tasks or grammaticality judgment tasks, which correlates with their ability to account for the human neural and behavioral data. So we see this blue bar here, which shows a positive and significant correlation between the model's ability to predict human neural data and its performance on next word prediction, but not its performance on other linguistic tasks. The correlation between these and the model's ability to predict human neural data is non-significant, shown with these gray bars, and this finding has also been replicated for behavioral data. So this is really exciting because it shows that these models, which have just been trained to maximally effectively predict the next word given the context, can actually account for a lot of the variability in human neural and behavioral data. However, the research which I've been presenting so far focuses on the ability of these models to predict human neural and behavioral data during the processing of fairly simple sentences, such as the ones shown here. And the picture becomes a little bit more complicated when we look at complex structures, such as garden path sentences. So garden path sentences involve some form of temporary ambiguity, such that when the less preferred, that's the less probable path ultimately appears in the input, there is some kind of processing difficulty. And the language models are still able to really effectively localize human sentence processing difficulty to the right part of these garden path constructions, but they severely underestimate the magnitude of this difficulty. So on this visualization, we see two LMs with different architectures. In blue, we see an LSTM with a recurrent neural network architecture. In pink, we see the GPT model with the transformer architecture. And both of these models severely underestimate the magnitude of the processing difficulty which is experienced on these structures by human participants during psycholinguistic experiments, which is shown with the green bars. And the authors of this paper suggest that this is because language models have what they call a one-stage model of language processing. So language models consider all structural analyses, all possible structural analyses of a parse. They maintain these actively in parallel, such that when the less preferred, the less probable continuation appears in the input, they predict processing difficulty, which is relative to the difference in the likelihood between the most probable continuation and what ultimately appears in the input. However, a much more likely hypothesis for how humans process language is that we don't hold active all possible structural analyses of a parse simultaneously, because this is computationally very expensive, and we don't have enough resources to dedicate to sentence processing in order to do this. So when a less preferred, a less probable continuation appears in the input, we experience processing difficulty just because of the decreased likelihood of this continuation. But then human parsers have to form a structural analysis of this parse based on their memory of the preceding context. And this is difficult because our memory of the preceding context isn't perfect. And these models of sentence processing have been referred to as two-stage models, and it's the revision processes which take place during this second stage which can kind of explain the divergence between the difficulty predicted by language models and that which is experienced by humans, because these revision mechanisms kind of are determined to a large extent by our memory constraints, and these memory constraints might not be accurately represented in the architecture of language models. So we wanted to find out more about how memory constraints shape the mechanisms we use for sentence processing, beyond just looking at sentences which involve some kind of difficulty due to revision. So we wanted to look at the processing of syntactically complex structures more generally. So we asked about the structural preferences of parsers during the processing of local and non-local filler gap dependencies. For our filler gap structures, we used relative clauses where the filler is dependent on the gap location in order to be thematically interpreted. So first, we asked whether human parsers had a preference for an early, a subject gap integration, or a later, an object gap integration in the case of local and non-local filler gap dependencies. This is an example of the stimuli that we used. So we have two conditions, a non-local and a local condition. The two different conditions contain essentially the same lexical items. The only difference is that the embedded clause, which is underlined, which appears between the filler and the relative clause in the non-local structure, the teacher remarked, has been moved to the beginning of the sentence in the local dependency, such that the filler immediately precedes the relative clause. We can see the subject gap continuations in red, the object gap continuations in blue, and across both dependency types, and regardless of where the gap appeared in the structure, the matrix clause continuation was the same. So we actually had this manipulation for dependency length across two experiments, so it was a between subjects manipulation. For both experiments, we recruited our participants using the web-based platform Prolific. Our participants completed an online version of the modified maze task, which I will explain to you in a few slides' time. In both conditions, our participants saw 48 critical items and 72 distractor items. We generated the ungrammatical foils for the maze task using this language model, and then we hand-sorted them. And finally, I just wanted to mention that we did also have a manipulation for filler animacy, which isn't relevant to the research questions which I'll be exploring here, but it is included as a predictor in our models. So to explore whether our human parsers had a preference for a subject or an object gap, we used an innovation to the maze task. So standardly in the maze task, at every single word in a sentence, participants are required to choose between a grammatical and an ungrammatical word with which to continue the sentence. So in this example, it's the first word in the sentence. It's really hard to find an ungrammatical kind of alternative for this. So participants choose between the and XXX. And then at the second word, the there is ungrammatical, so participants choose the girl who the teacher remarked. And we kept this standard choice between the grammatical and ungrammatical sentence continuations at every single word in the sentence until our participants reached a decision point where we gave them the choice between two possible grammatical continuations. One continuation was consistent with a structure with a subject gap. This was always an auxiliary verb. And the other choice was consistent with a structure with an object gap. This was always a determiner, actually always the or a. And regardless of the continuation, which our participants chose, they were able to continue with the pass. And this allowed us to tap into Parsers' preferences directly. So we found that our human parsers had a preference for subject over object gaps consistently in both dependency types, but that this preference was much stronger in the case of the non-local dependency. And this is consistent with the active filler strategy. The active filler strategy posits that when processing filler gap dependencies, parsers have a preference to integrate the filler in the earliest possible gap location before there's evidence even of a gap being present here from the input. So next, we wanted to see whether this preference for a subject gap, which is heightened in the condition with the non-local dependency, could be predicted by surprisal values generated by language models. So we used GPT-2 small because there's evidence that this is the language model which best predicts human reading time data. And we generated surprisal values for the two words which our human participants saw at the decision point in the maze task. So the auxiliary, which was consistent with a subject gap continuation, and the determiner, which was consistent with an object gap continuation. And given that surprisal is the negative log probability given the context, we solved the equation for surprisal to find the probability of a subject gap pass given just two possible continuations, a subject gap or an object gap pass. And normalizing our data in this way was really important because in the maze task, our human participants had only a choice between one of two options, whereas our language model at the decision point could generate any given word that it had in its vocabulary. So we ended up with the probability of a subject gap pass in our human data and the probability of a subject gap pass in our language model data. And having this data on the same scale was really important because it eliminated the need for a linking function, which makes additional assumptions about the data, as we would need, for example, if we were linking surprisal values to reading time data. So we wanted to see whether the probability of a subject gap pass from predicted by our language model could predict the preference for a subject gap pass in our human data. And we found that, surprise, although the language model could predict the human preference for a subject gap in the case of the local dependency, it failed to predict the preference for a subject gap in the human data in the case of the non-local dependency. Specifically, the language model really underestimated the strength of the subject gap preference in the human data in the case of the non-local dependency. It predicted a preference about on par with what it predicted in the case of the local dependency, whereas from the human data we can see that actually the strength of the subject gap preference is really much higher in the human data in the case of the non-local dependency. So we wanted to try and explain what was driving this mismatch between the strength of the subject gap preference predicted by the language model and the much higher preference that we found in our human data. So one potential explanation that we thought of is that this active filler strategy, so the pressure to offload the filler in the earliest possible gap location, was being driven by memory considerations. So maintaining a filler in memory or storing it in memory without a thematic role before it can be thematically integrated with the rest of the pass and interpreted relative to its meaning is costly. In a structure, such as with the case of the local dependency, processing costs on the rest of the sentence are relatively low. So having this additional burden before the filler can be integrated into the gap position isn't really highly problematic for the parser. Contrastingly, in the case of the non-local dependency, the processing cost on the rest of the structure is already high. So then the human parser feels an increased pressure to kind of relieve itself of the memory burden that's associated with maintaining, storing this filler in memory by integrating it into a gap location as soon as possible. So we wanted to see whether we could use computerized language models to kind of provide evidence for our hypothesis that this heightened subject gap preference in the case of the non-local dependency was being driven by memory considerations. And so initially we were thinking about introducing somehow memory constraints into the architecture of our language model to see if it could better predict the human data in the case of the non-local dependency. However, we had some concerns, so we weren't sure whether language models which included some element of forgetting in their architecture, such as lossy context surprisal, could be generated out of the box to our stimuli. This is because as the memory kind of constraints on a language model increase, so does the probability that the language model is actually going to forget the dependency altogether. And in the case of our subject gap sentences, if the model forgets about the presence of the dependency, it's left to predict surprisal on the auxiliary should in the string the teacher remarked should. And this is a relatively unlikely string because you have two verbs directly following one another. The auxiliary follows the main verb. Contrastingly, in the sentence with the object gap, if the language model forgets about the presence of the dependency, you have the string the teacher remarked to the department, and this is a fairly likely string. You can imagine it continuing. The teacher remarked the department should increase funding. So we were worried that actually by introducing memory constraints to our model, we would pull our effect in the opposite direction and increase even more the preference for object gaps in our language model data. So we thought about some kind of roundabout ways which we could provide evidence that memory considerations were driving this heightened subject gap preference. And this is where our ideas get a little bit more tentative. So if you have any ideas or suggestions, I would love to hear them during the discussion. But we thought we could take an indirect approach to showing that memory constraints were important for driving this active filler strategy, the preference for an early gap. So we thought that we could demonstrate some kind of cost for offloading the filler later, as in the object gap, rather than sooner, in a model that has memory limitations compared to a normal language model which isn't limited relative to its memory. And we thought this could offer kind of an explanation as well for the existence of the active filler strategy. So our resource rational parser opts for an early integration after foreseeing kind of a cost of integrating further downstream. Maybe this makes the parse more error-prone, or there's a chance of forgetting the dependency. Okay, so to summarize, we have presented a case where surprisal values generated by language models do not align with the preferences of human parsers. We've demonstrated this as the inability of language models to predict this really heightened preference for a subject gap in the case of non-local dependencies. We've hypothesized that a reason for this misalignment between surprisal values generated by language models and what we find in our human data could be that the preference to offload the filler early is being driven by memory considerations, kind of subsumed as part of this active filler strategy. And these memory considerations aren't accurately reflected in the architecture of the language model. And in doing so, we've kind of extended the work of looking at misalignments between what's predicted by language models and what's predicted by humans beyond just sentences, which involve some kind of revision difficulty. And finally, we've presented some avenues for exploring our hypothesis further with regards to testing whether it is these memory constraints which are driving the subject gap preference. We've talked about some potential concerns we foresee and some ideas possibly to kind of get around them. These are my references, and I'm now happy to take questions.
Hi there, John Brennan, University of Michigan. Thank you. I really appreciate the kind of drive to look for mismatches as an opportunity for theory building. And I'm very sympathetic also to the role of memory might play, but I want to push a little bit at a possible alternative. So 20 years ago, when at the early, when Surprisal was first being considered as a linking hypothesis to think about human processing difficulty, the earliest models also found that Surprisal didn't capture relative clause preferences. This is when Surprisal was calculated over structures rather than strings, as in LLM, but the intuition was already there. Surprisal doesn't cut it. And instead of looking at memory, an alternative was this idea of entropy reduction. So not just the entropy of the context, but entropy reduction. And I wonder what thoughts you might have about sort of the relative possibility of go towards memory, or is there still a way just within the information kind of theory world that to kind of get at these asymmetries that you're seeing? Thank you.
So I was on the plane here reading about entropy, and after I arrived, we discussed looking at entropy and seeing whether changes in entropy could predict the difference that we're seeing between the language model data and the human data in a better way than Surprisal could. So it's actually one of our avenues for future research, and as of yet, I don't have any specific thoughts about it, but yeah, I would love to see if it's a better predictor of our data. Thank you.
Hi, thank you. Lisa Levinson, University of Michigan. My question is less on the broader narrative level, but more about the maze task, and I think about the estimates of the preferences that you're getting out of that, the innovation in the maze task, that aspect. So you're putting kind of a type of forced choice into the maze, but in the maze task, strategically, in the normal maze trials, if you find something good, then you can move on. You can choose that. And there's nothing that compels you to look at the other option at all, right? So I would think that most of the time, if participants find the right option, they'll just click that and they'll proceed. So given that mindset in the maze task, then there's going to be some influence of, which thing they see first, which I assume you counterbalanced or something like that. But I think that would still affect the estimate because people don't necessarily look, as far as we know, look left first or right first. I think probably different participants have different strategies. It might depend which one was correct last or whatever. So I don't think we really know what side people would look at first and how that would impact their choices. So I was just wondering if you had any thoughts to address that, or or if that's just sort of a kind of acceptable noise in the estimates at this point.
So I agree with you to the extent that this is forcing a binary choice, and maybe, they considered the object gap, but then ultimately went with the subject gap, although we did request feedback from our participants, and none of our participants actually noted that there was 2 grammatical choices at any point in the maze. We also did a...
You said none of them?
Yeah, none of them.
So I think my question was the opposite. So I think that that is exactly what I think is happening, that they're not noticing, because they only see that there is one choice. So they're much more often just going to pick the first thing they see because it's possible.
Well,
and so then you would have an influence of, the thing that's going to be picked most is the thing that they see first, which is going to be, we don't know which one that even is.
So we did 2 analyses, which I think might help in answering this question. We did a by-participant analysis to see whether there were participants that consistently only chose subject gaps and ones which were more variable in their responses, and we didn't find this. So we found that this preference that we're demonstrating here was fairly consistently reflected in the preferences of individual participants as well. We also looked at whether participants were more likely to choose the subject gap continuation depending on whether it appeared on the left or the right of the screen, and whether it appeared on the same side of the screen as the previous grammatical continuation. So if the previous grammatical continuation was on the right, whether they were more likely to pick the subject gap continuation if it appeared on the right, and we found that they weren't. So I hope that goes some way towards answering your question.
Yeah, I think that addresses some aspects of it. I think there's still some degree, because we don't know where they look first, of there's going to be, just like the accuracy of that estimate of like what really the different, like I don't think it's going to affect the sign of the effect, or the direction, but that there's going to be things unknown of when people are doing that. But thank you.
Thank you.
Hi, thank you for the talk. I'm just throwing this out there as a suggestion, maybe on the methods side with the language models. I was wondering if you might consider, for evaluating the probabilities, looking at sort of a broader set of words that are consistent with the subject or the object continuation, rather than just those 2 words, just to handle the fact that the language model surprisal values might be kind of noisy and depend on training, and so you might take like the set of words that could be compatible with the subject continuation, the set of words that could be compatible with the object continuation, sort of sum those probabilities and compare them. So you're getting a sort of perhaps a bit less noisy estimate of sort of the total probability mass that the language model assigns to continuing in the subject in any way versus continuing as an object in any way. I'm not sure how that would exactly relate to the humans, but it might potentially address like some of the noise with estimating these from the model. I don't know if that's something you might consider.
Yeah, so something we considered was that was possibly happening with our human data is that our humans were predicting something like, okay, next I want to see a verb, and then they were choosing the word that was most compatible with like this prediction, regardless of whether it was like should or might, so that they weren't predicting specific lexical items, but rather like syntactic categories, parts of speech. So then we were thinking about looking at language models which use previous context to predict like the syntactic category or the part of speech of the next word rather than specific lexical items. We got a bit stuck on the details in terms of just like, there are many possible words which are technically compatible with an object gap continuation and a subject gap continuation. It's not just like all determiners, right? It's also a noun could be compatible with an object gap continuation. So yeah, I think we would need to think hard about how to narrow down the number of options that we consider as being compatible with a subject gap and an object gap continuation. But yeah, that's something we're thinking about.
Yeah.
Thank you so much.
Thank you.